Now, a strain energy density, so I'm going to write it here. Strain energy density and stress are dimensionally equal and can be expressed in the same unit. So strain energy density and stress are dimensionally equal and can be expressed in the same units. Now, we have a strain energy and strain energy density. Now, going back to our strain energy, which behaves in the elastic region. So, if we are in the elastic region, so let's go back to our lecture right here. So, if we are in the elastic region, which is this guy right here. So, if we are in the elastic region, we can use our Young's modulus, which is E. So Young's modulus or modulus of elasticity can be described by E uh, by sigma x E epsilon x. So again, if you go back to your mechanics of materials 1, E is equal to stress over your amount of strain, and it's just basically the same right here. Now, based on this description of your elastic modulus, we can now define our strain energy in the elastic region. So now, strain energy density, it's now equal to from 0 to epsilon 1. So we have sigma x. I'm just rewriting the one on top right here. Dx. Now, that's equal to from 0 to epsilon 1. Now, we can replace this sigma sigma x right here as E epsilon x d epsilon x. Now we can further simplify this one. So we can say that our strain energy U is equal to E epsilon 1. Now this becomes square. This becomes over 2 based on our integral right there. Now, or we can say that our strain energy density is equal to sigma, let's call it 1 square divided by 2e. Now, again, it's just working with the equation with using this one right here. Again, we are writing this equation based on our assumption that we are maintaining our force or our stress in the elastic region. So we are only up to this region right here. Now that we know what's a description of our strain energy and a strain energy density, let's define other terms which may not be useful to your exam, but it's good to know that they exist. So the first thing is your modulus of resilience. What do you mean by modulus of resilience? If we talk about resilience, we are talking about the elastic property. Now for modulus of resilience, now instead of taking the force displacement curve, for modulus of resilience, now we need stress and strain curve. Now that's a major difference. Again, we are now taking stress strain here. Note that on the top, when we measured all the area, it's based on your P and the X, which is your force and your displacement. Let's go back to modulus of resilience. So if we have stress strain curve, how can we calculate for modulus of resilience, which is denoted by U sub y, and that's equal to square of your stress divided by 2e. Now, This equation right here, it's described by this area of your curve, which is just your elastic region. If you take the area of the elastic region, you'll end up with this equation right here. So that's the definition of your modulus of resilience. Now, how about the modulus of toughness? Now, for modulus of toughness, now it's a combination of your elastic and plastic region. So that's elastic plus plastic property. So this is the energy per unit volume required for the material to rupture or to fracture. Now again, for modulus of toughness, we have to write our stress strain curve. Now we have this curve right here. And then let's say it fractures at this specific spot. Now we can take the area of our curve, and that's described by U times or U sub R. Your R means your rupture. So now again, you will just have to apply your integral. So if you're going to calculate for the area, you can U sub R is equal to, let's say, from 0 to strain 1 stress d epsilon, let's say 1, and then you will be able to get the area of your curve. So now we defined four different things: strain energy density, modulus of resilience, and modulus of toughness. Now, let's move to the next one. Now, our overall objective here is to get an equation of your elastic energy, which is U. Now, we assume an axial loading, so we have a member, and then we pull it by a certain amount of force P. Now, let's now go to strain energy under axial loading. Now, if we go back to our equations, we know that our small u is equal to 1/2 E epsilon x squared. And I think we define it up here, so we have our small u, it's 1/2. So it's going to put red, so 1/2 ex squared. So if we go back to our equation, it's this guy right here. Now that's our strain energy density. Now, if we're going to, so this is also has the same form as 1/2 sigma x squared over E, which is again similar to the one we wrote on top. Now we change the convention to x because we assume that the force is being applied to the x-axis right here. So that's the only difference, nothing fancy. So we assume that it's epsilon x and sigma x. Now that's the energy. Now we have to define our strain energy U. Now for strain energy U, note that for U we can say that it's the integral of our small u times dV. So basically it's your strain energy density is equal to your energy itself divided by your volume, so it's the same thing. Now if we're going to apply this equation right here, so we have u on top, we have our dV, we can say that our strain energy is equal to sigma x squared divided by 2e a times dx. And why did I change this as a dx? So that's dv. So we can say that the dv is equal to area times dx. Now that we have that equation, so we can also say that our u, sorry, I should not underline this one because that's a capital U. So, so our capital U is also equal to P square divided by 2EA square ADX. And how did I change this form right here into this one? It's just a matter of assuming that our stress is equal to P over A. And that's it. So we have that specific form. Now that we have that specific form, so we can also say that this strain energy can be calculated from 0 to L. So from 0 position of your member up to length L, P square over 2 EA dx. Now, if we're going to solve this integral right here, we are left with P squared L over 2EA. Now, that's the equation to get the strain energy if we have eggshell loading. Now, if we're going to go back to the slides, just minimize right here. So again, we calculated this. So for eggshell loading, we have our energy is equal to P squared L divided by 2AE. And we're going to show how to calculate our strain energy. And if you look at the equation right here, strain energy, it's dependent on the length, amount of force, area, and your elastic modulus. Again, we are assuming that we are applying force in the elastic region, not in the plastic region for these equations. Now, that's for eggshell loading. We have different types of loading. I'm not going to derive everything here. So you can check your book in chapter 11 for derivation. So we have eggshell loading, we have bending, we have shearing, we have torsion. And if we're going to apply the same concept that we did, you're going to end with the following equations. So for our class, you're going to solve problems and you're going to need these equations to calculate for the strain energy. Now, in order for you to understand what's the essence of this equations right here, let's probably do some practice problem. So which is, I think, the next slide here. So concept application 1. So a rod consists of two portions, BC and CD, of the same material, same length, but of different cross sections. Now determine the strain energy of the rod when it is subjected to a centric axial load P, so that's P in compression, expressing the result in terms of P, L, E, the cross-sectional area A of portion CD, so that's your CD, and ratio N of the two diameters. So again, we put this one as N square A, and that's our A, that's a smaller section of your sample. So based on this given right here, we have to calculate our strain energy. Now, this is axial loading P. If we go back to our equation, I think, okay, sorry. Okay, let's go back here. So we have axial loading is U, the equation is U is equal to P squared L divided by 2EA. So I'm going to drag my screen right here. So concept application 1. So we're going to use equation U is equal to P squared L divided by 2AE. Now, next slide. So now we have two sections, BC and CD. Now, if we're going to divide our section into two, so we have the first one is with area A, and the length right there is 1/2 L. So we have A and 1/2 L for the length. Again, we are taking the area and length because if we check our equation here, we need area and length. Now that's the first section. We move to the second section. So for the second section, we have a bigger cross-sectional area And your area, it's defined by n squared a, and it has again same length as your CD, so that's 1/2 L. So this is just to be clear, so this is BC, from B to C, and this is C to D. So we have two different sections. So how can we calculate for our strain energy? Now, since we have a certain amount of section B, C, D, so first let's calculate the strain energy in the section B, C. So if we're going to calculate the strain energy in the BC, so our equation for strain energy is P squared. So again, we are applying force P, so we use the same amount P. So P squared, and our length is 1/2 L divided by 2AE, so that's 2. Area is n squared A, and E is whatever the modulus of elasticity of that cross section. So this is for section BC. Now we have to add another one with different cross section. So in this case, we're going to use the same equation, P squared 1/2 L divided by 2AE. So that's just A and and E. And for that one, that corresponds to section CD. If we're going to solve for the strain energy of the whole section, that's equivalent to P squared L divided by 4AE, and that's 1 plus 1 over n squared. Or we can also say that U is equal to 1 plus n squared 2n squared times P squared L divided by 2AE. And just note that this comes from this equation right here. And this is the dependence if you have a different section, if you have n squared right there. And if you check, let's say you assume that n is equal to 1, you have the same cross-sectional area, you will end up with just this equation right here. Now, that's super easy for concept application number 1. Let's move to concept application number 2. I think we have 4 or 5 examples right here. So concept application number 2. So drag my screen here. Okay, one more. Yeah. Concept application 2. So a load P is supported at B by 2 rods of the same material and of the same uniform cross section of A. Determine the strain energy of the system. So we're talking about the whole system right here. Now for concept application number 2, again, our objective is to find our strain energy U, which we don't know at the moment. Now, if we're going to look at the loading condition on the left, we have force P, and we can calculate for the corresponding amount of force along CP, along BD, and along your CD, which is just your P. And then based on that forces, now you can calculate for your internal for your strain energy. So let's do that and solve the problem. So the first thing here is so that's point C, that's point B. It forms a triangle right here. That's point D. And then we have this length right here. So this is so there's 3, 4 right here, and then another right here, which is this is 3 and 4. Now based on that one, you can calculate for all your lengths, but first let's draw our free body diagram. So based on this, we have applied P right here. So we have force at BC, and then can also have, so it should be going up because going down it's countering the effect of your P. So this should be F B D. Now we have this force system, and then you can now calculate what would be the equivalent force in BC and FDB. And then you will find out that, so I'll trust you that you can still remember your mechanics of materials 1. So in this case, we can say that our FBC, that's all our BC as a result of our P, is equivalent to 0.6 the amount of P. Now, your FBD is equal to 0.8 of your P. So you now have forces along here and then forces along there. Now we have all the forces. We have axial loading for our equation, and if we're going to go back to our equation, your U is equal to P squared L divided by 2 EA or AE. So for axial loading. Now in this system you have two sections, section BC and section DB, which means I could split my U as equal to FBC square and then length BC, and then divided by 2 EA, plus I'm going to have FBD square LBD divided by 2 EA. Now you have this equation right here. So what's going to be the length of your BC and LBD? So in this case, note that this is L right here. So what you will get for DB is, or BD is 0.8 L. Oops, that should be L. So that should be, oops, it's eraser. That should be L. And here you will get for a BC, that would be 0.6 L. So based on those lengths, we can now go back to our equation and substitute the number. So for your strain energy U, that's going to be equal to FBC square. So our FBC is 0.6 P square. LBC is 0.6 L divided by 2 EA plus FBD square, so that's 0.8 P square, 0.8 L divided by 2 EA. Now our U, if you're going to calculate this one, it's going to be equal to 0.364 P square, it's L divided by AE. So it's going to box this one. So that's going to be your answer for concept application number 2. So the first two examples that we have were we used the equation for axial loading. So I believe the next one would be for a different type of loading. Again, if we go back to the slides, slide number 2, I think. Oops, it's not going back. Yeah, so we have axial loading. We have axial loading. We have oops, I think it's gone. Okay, I lost my file previously. So now when we're dealing with different types of loading, so we have axial, we have bending, shearing, and torsion. So the first two examples only covers axial loading. So now let's move to the third example, which is related to bending. So determine the strain energy of the prismatic cantilever beam AB, taking into account only the effect of normal stress. So we have a beam AB, we have a force P. Now it's related to bending, normal stress, which means it's more related to the bending of your beam. Now let's go to this guy right here. So first, let's recall the equation for our bending. So for bending, we have U is equal to from 0 to L m square to E I dx. So we didn't derive this equation, but I showed you the result if you're going to derive the equation for your bending. So this is the strain energy as a result of bending. Now, from this equation, we need m, which is our moment. Now, how can we get the moment from our beam? Again, going back to our discussion on beams, we can cut our beam and get the expression for our moment. So this is the beam from the left. That's the force P. Now we can cut our beam and get the equation for our moment. So here, let's cut the beam in this section right here. And eventually, you will get m is equal to negative px. Now, you would imagine that if I cut my beam just before my force, right here, it would have the same equation, like this. So, up to almost the entire length of the beam have this equation for your moment, which is defined by P and X. And let's say your X is equal to 0 at the end of your beam on the left side. Now, using this equation here, we can now calculate for our strain energy of our beam. So now our U is equal to from 0 to L, that's the full length of our beam, and this equation holds up from point A to point B, which means we have P squared X squared divided by 2 EI dx. And based on this loading condition, we will get U is equal to P squared L3 divided by 6 EI. Now that's going to be the answer for this question. So you can see this strain energy calculation, it's very simple if you're going to only use the equations that I showed you in, I think that's in the second slide. So yeah, just checking if that's the question right there. Now that's for the equation for bending. So we have another example here, which is I think for torsion. So now, let's go to concept application number 4. So a circular shaft consists of two portions, BC and CD, of the same material and length, but of different cross sections. Determine the strain energy of the shaft when it is subjected to a twisting couple T. So we have a torque T at the end of the beam, at the end of D. Express the results in terms of TLG, the polar moment of inertia J of the smaller section, and the ratio N of the two diameters. So again, that's ND, that's diameter D. And what do we mean by G and moment of inertia right here? If we go back to the equation of related to strain energy, if we check for torsion, we have T squared L to G J. Your G is your shear modulus. Now for your, so I'm just going to drag my screen. So now that's concept application 4, I think. So let's change concept application number 4. Now we're going to use equation for torsion, which has equation of U is equal to E squared L divided by 2GJ, to polar moment of inertia. Now let's go back to the concept application number 2. So we have this specific circular shaft, and our objective is to calculate for the strain energy in on the circular shaft. Now first, similar to what we did previously, so this is section BC. Oops, I don't have my screen yet. Okay, so section BC. So we also have section CD, and for section BC we have diameter ND. For CD we have diameter D. So we have again different sections. So that's smaller, that's a larger circle. Now for strain energy, again we can divide it into two sections, BC and CD. So I could get my strain energy for my BC plus my strain energy for my CD. Now this is torsion, and we know the equation for strain energy if we have a torsion. So based on strain energy equation, we can say that this is T squared L. Oops, should erase that one. Okay, go back. T squared L over 2J, and that's for BC, plus E squared L 2GJ, that's for CD. Now both of them have lengths of 1/2 L, so which means our L right here, that's 1/2 L. Now we know that we are applying T, which is correct, so we have both T's for BC and CD. Now we have our polar moment of inertia right here, and this is a little bit different because we have, for polar moment of inertia, we know that the equation here is J is equal to 1/2 pi r/4. Now note that BC has a diameter of ND, and we have CD that has a diameter of D. Now, based on this, we can account for all of these numbers right here, and then we'll end up with the following equation. So we can get 2T squared L 4GJ 1 plus 1 over n is to 4, which is this equation right here. And again, similar to the previous one, if you look at this equation, it consists of two parts. You look at the equation of your torsion, it's kind of similar right there. So for n is equal to 1, you will end up, which has the same diameter BC and CD, you will end up with the original equation. So that's how you're going to deal with the problems with a certain section with different diameters. So you have to section it BC and CD and then calculate for the strain energy. Now let's go to the next example. Next example. Okay, now. Okay, so concept application number 5, taking into account only the effect of normal stress due to bending, determine the strain energy of the prismatic beam AB for the loading shown. Now, and then B, evaluate the strain energy knowing that the beam is with this dimensions, and then P is equal to 40 kips, length A, B, and E, which is these numbers. Now, in the first 4 problems, we use variables. In this case, once we calculate for our strain energy, we can plug in those numbers into our equation in order to find a solution to our problem. Now, let's solve this one here. Let's drag board again. So now for this one, we are given with the beam with, so this is concept application 5. So we have this beam. So we have it's point A. We have rollers at point B. And then we have applied force P, and this is A, and that's going to be section B. Now the question there is to use the bending equation. So just assume that we only have bending to determine the strain energy. Now for the bending equation, we use it in a previous problem. So our strain energy is equal to 0 to L m squared 2 EI dx. Now, this is dependent on the values of your moment right here. The problem with this type of problem is that, again, if we're going to take the value of our moment, our approach is to cut a beam. So let's say we cut it right here. Now, if we cut our beam right here, we solve for the moment, we have support reactions at A, and we only have up to this point. Now, the problem for this one is as you move from this point, which is at the point where your P is located, up to this point, now the equation of your moment changes from the left side of your P going into the right side. Because if you cut this beam right here, you're going to get only support reaction. So I'm going to call it RA. So you only have this one right here. And if you're going to cut it on the right side of your P, note that you're going to get something like this. So you have P, you have RA, and then you're going to get different equations for your moment. So in this case, we have to treat this beam separately. So first, we have to calculate the energy along the AD, and then energy at DB, and then add them together, and then we're going to get the total strain energy for our system. Now let's do that. So first, let's look at section AD. So let's say section A to D. So for section A to D, we only have support reactions RA, and then we have this, we have our moment. We can call it M sub 1. We can say that M sub 1 is equal to so RA times your X. Now for your section DB, so we have this guy right here. So now we call this section as our X. Now for section DB, we have the following. So we have this. So for section DB, to make it simple, instead of cutting it on the left, we can assume that this is going to be our point B. So instead of cutting it right here on the left and then making our A as 0, to simplify the problem, we can assume for the second equation that our reference point is our point B, which means that I cannot call it as X. I can now call it, call it as V. You will see later that this is kind of the same. It's just one assumption for AD. So for AD, we assume that our reference axis or reference point is A. For DB, our reference point is at point B. So that's why we call them differently. So in this case, we call it V, we called it X right here. Let's go back to the problem. So we have, let's say, shear right here. Oops, change it to blue. And then we have M2. So your M2 is equal to RB times your small V. So you have RA and RB, which you can solve from your beam right here. So you have your P, you have two support reactions, so you can sum the forces along your Y, get a specific moment at specific point, and then you will end up with the following numbers. So eventually you will get that your support reaction at A is equal to P times B divided by L, which is of course pointing upwards. Now your reaction at B is equal to P times A divided by L. Again, this is pointing upwards. Now if we're going to substitute those numbers in our moment, so the first moment would be for section AD. So our RA is P B over L X. So that's the first moment. Now for moment number 2, we can say that this is now equal to PA over L times V. So again, this is two different assumptions. Note that we are treating them separately. You want to calculate the strain energy for AD. Now you want to calculate separately the strain energy for DB. So again, you can have a different reference point if you do this method. So now let's calculate for our for our strain energy U. For strain energy U, that's equivalent to U AD plus UDB. So for A to D, so from 0 to A, so we have M1. So from 0 to A, this one prevails right here, M1. So it's M1 square 2EI now dx plus, now from 0 to B, so now our 0 to B is from this point up to this point right here. Again, we section the beam right here, making our reference point as a 0 at point B. So we section right here. So that's from 0 to B. Again, that's a reference point. It's not A, it's from B. So we have M2 square 2EI. Now this is dV because we made a different assumption right here. Now, if we're going to calculate for this equation here, we're going to get 1/2 EI 0 to A BB LX, that's all square dx plus 1 to EI, again 0 to B BAL, that's now V squared dV, and then you will end up with the following. So that's 1/2 EI B square L square, you have B square A cube 8 plus A square B cube 3, and that's equivalent to, so this is the simplified version, so you're going to get strain energy equal to P square A square B square 6 EI L square A plus B. So now you have that final equation for your for strain energy. So now that you have that one, you can calculate for your specific number or strain energy using the numbers right here. Now let's do that using this equation here. Okay. Now let's do that. So now your U is equal to this equation. Now take note that A plus B right there. If we're going to go back to our problem, A plus B is also equal to L, which means I can cancel a plus b and remove that square right there. So I can simply say that my strain energy is equal to u p square a square b square divided by 6 EIL. So again, it's because of this one that's equivalent to L. Now let's write the given uh, number. So for P is equal to 40 kips, A is equal to 3 feet, which is equal to 36 inches. So we have our E, modulus of elasticity, 29 times 10, 6 psi. So we have our L is equal to 12 feet, which is equal to 144 inches. So our B is equal to 9 feet, which is equal to 108 inches. Our I is equal to 248 inch raised to 4. Now, using all those numbers, which is again just given in the problem right here. So you have U is equal to 40 kips square, 36 inch square, 108 inch square divided by 6, 29 times 10 raised to 6 psi, 248 inches raised to 4, and 144 inch. And that will give you a value of 3.89 inch. It's right here. So that would be the final answer for concept application number 5. Yeah, it's concept application number 5. So now we've used the first one, eggshell. We used the bending. Now we also use the torsion. In this case, this is the bending. Again, for bending, you have to get the equation of your moment. In this case, we get two equations from AD to DB and assume a different reference point. Again, we can treat them separately, so that's why we can assume a reference point for AD as A at A is equal to 0. And for the second one, DB, we can assume that our reference point is at point B. So I have another example right here. I think this is the last one. So concept application number 6. So during a routine manufacturing operation, rod AB, which is on the left, must acquire an elastic strain energy of 120 H-pound. Using elastic modulus 29 times 10 raised to 6 psi, determine the required yield strength of the steel if the factor of safety is 5 with respect to permanent deformation. So here I'm going to show you how to apply the factor of safety if we have this type of problem. We have all the numbers, 5 feet, 3/4 inch diameter of the section. We are applying P, which means it's eggshell loading. So let's calculate this problem. So it's going to drag the screen. So this is concept application number 6. So which is going to be the last one. So for concept application number 6, we have factor of safety, which is equal to 5. Our E is equal to 29 times 10 raised to 6 psi. And we have our U, which is strain energy 120 inch pound. And then we have this equation, these numbers right here. Just checking if this will work. Yeah. So the first thing is we have to consider our factor of safety. So since factor of safety is equal to 5, so we have the rod must be designed higher to have a higher hue. Now, U is equal now to 5 times 120 inch pound, and that's now equivalent to 600 inch pound right there. Now, so the required yield strength. So we're talking about yield strength here. So now we have unknown as our yield strength. Now, we now get a volume of our rod. Why do we need to get a volume? So we know that our strain energy density, small u, is equal to sigma y squared divided by 2e. Now, based on this, we can get our, so we can get the yield stress of our material. Now, this is not for your strain energy. This is actually for your, sorry for that. This is for the equation for your modulus of resilience. So that's the equation that we derived earlier. So we have the equation for modulus of resilience, which is sigma y squared divided by 2e, and we can calculate our yield stress based on this sigma y right here. But first, let's define what's u. So that would be that's our target strain energy. So the volume is V is equal to A times L, and that's equivalent to pi over 4. We have 0.75 inch, that's square, so that's the area. So we have the length is 5 feet, but we can convert it to inch, so that would be 60 inch. So that's the length, and that's equivalent to 26.5 cubic inch. So that's going to be the volume of our material. Now, if we're going to calculate for our strain energy density, which is small u, that's equal to capital U times our volume. Our capital U is 600 inch pound divided by 26.5 inch raised to 3. Now that's going to be equal to 22.6 inch pound inch cube. Now this U right here, it's actually equal to your modulus of resilience, so we can say that that's equivalent to sigma y squared divided by 2e. Now based on this, you can just plug in the numbers, so you have your U, which is 22.6 inch pound inch cube is equal to y squared 2. So you have 29 times 10, 6 psi. So now your yield is equal to 36.2 ksi. So that will be the final answer for concept application number 6. So checking question: determine the required yield strength of the steel if the factor of safety is 5 with respect to permanent deformation. So we need this yield strength for this specific loading condition right here. Now that's the end for the strain energy. Unfortunately, we don't have much time this term, so this is going to be the end for chapter 11. So I'm going to send you an email for updates regarding your final exam and the coverage for the questions. Again, thank you.